Hi everyone, I'm Yuzhe from MIT. I'll be presenting Change is Hard, a closer look at subpopulation shift. This is a joint work with Haran, Dina, and Marzi. Machine learning models often perform poorly on subgroups that are underrepresented in the training data. For example, in the task of cow and camel classification, cows are often found in areas with green grass, and camels are often found in areas with yellow sand. However, such correlation is spurious because the presence of cows or camels is unrelated to the background color. As a result, the trained model performs well on the aforementioned images, but cannot generalize to animals with different background colors that are rare in the training data, such as cows on sand or camels on grass. In addition, when it comes to medical diagnosis, studies have found that machine learning models often perform worse on underrepresented age or ethnicity groups, raising important fairness concerns. All these shifts have been generally referred to as subpopulation shift, but little is understood on the variation in mechanisms that cause subpopulation shifts and how algorithms generalize across such diverse shifts at scale. So, how to model subpopulation shift? In this work, we provide a fine-grained analysis and benchmark on subpopulation shift. We first provide a unified framework for subpopulation shift modeling. In classic classification setup, we have training data from multiple classes, where here we use different color densities to represent number of samples in each class. However, when it comes to subpopulation shift, there exist attributes in addition to class, such as the background colors in the cow-camel problem. In this case, we could define the discrete subpopulations based on the attribute and the label. And here, the number of samples for different attributes within the same class could also vary. And naturally, to test the model, similar to the classification setting that we evaluate performance across all classes, in subpopulation shift, we test the model across all subgroups to ensure the worst performance over all groups is good enough, or ensure equally good performance across all subpopulations. Specifically, to provide a generic mathematical formulation, we first rewrite the classification model using Bayes' theorem. We further view each input X as being fully described or generated from a set of underlying core features X core and a list of attributes A. Here, X core denotes the underlying invariant components that are label specific and support robust classification, whereas attributes A may have inconsistent distributions and are not label specific. As such, we can integrate this modeling back to the equation and decompose it into three terms. The first term represents the pointwise mutual information between X core and Y, which is the robust indicator that related to the underlying class labels. The second and the third terms correspond to the potential bias arising in the attribute distribution and the label distribution, respectively. Such modeling explains how the attribute and the class influence the outcomes under subpopulation shift. Based on the formulation, we formally define and characterize four basic types of subpopulation shift. First, when certain attribute is spuriously correlated with label Y in training but not in the test data, it implies spurious correlations. Moreover, when certain attributes are sampled with a much smaller probability than others, it induces attribute imbalance. Similarly, class labels can exhibit imbalanced distributions, causing low preference for minority labels. This will lead to class imbalance. And finally, certain attributes can be totally missing in training but present in testing for certain classes, which motivates the need for attribute generalization. These four cases constitute the basic shift components and are important elements to explain complex subgroup shifts in real data. And in practice, datasets often consist of multiple types of shift simultaneously instead of one. Now, after setting up the formulation, we propose PBENCH a comprehensive benchmark including state-of-the-art algorithms evaluated on 12 real-world datasets. In particular, these datasets originated from different modalities and tasks, including vision, language, and healthcare applications, with data modalities range from natural images, text, clinical text, to chest X-rays. They also exhibit different shift components. With the established benchmark and over 10K trained models using 20 state-of-the-art algorithms, we reveal intriguing observations for future research. First, we observe that SOTA algorithms only improve subgroup robustness on certain types of shift, but not others. We plot here the worst group accuracy improvement over ERM for various state-of-the-art algorithms. For spurious correlations and class imbalance, existing algorithms can provide consistent worst group gains over ERM, indicating that progress has been made for tackling these two specific shifts. Interestingly, however, when it comes to attribute imbalance, little improvement is observed across datasets. In addition, the performance becomes even worse for attribute generalization. These findings stress that current advances are only made for specific shifts, while no progress has been made for the more challenging shifts such as AG. Further, we are motivated to explore the role of representation and classifier in subpopulation shift. In particular, we separate the whole network into two parts, the feature extractor F and the classifier G, where F extracts the latent features from the input and G outputs the final prediction. We ask the question, how do representation and classifier affect subgroup performance? First, given a base ERM model, when just optimizing the classifier learning with fixed representations, it can substantially improve the performance for spurious correlations and class imbalance, indicating that representations learned by ERM are already good enough. Interestingly, however, improving representation learning instead of classifier can bring notable gains for attribute imbalance, indicating that we may need more powerful features for certain shifts. Finally, no stratified learning manners lead to performance gains under attribute generalization. This highlights that one needs to consider the model pipeline design when facing different types of shift in reality. Furthermore, we observe that model selection and attribute availability considerably affect subpopulation shift evaluation. Specifically, when gradually removing the attribute annotations in training and/or validation data, all algorithms experience notable performance drops, especially when there's no attribute available in both training and validation. This indicates that the access to attributes still plays a significant role in getting reasonable performance in subpopulation shift, and future algorithms should consider more realistic scenarios for model selection and attribute availability. Finally, we reveal the fundamental trade-off between evaluation metrics. Worst group accuracy, or WGA, is considered as gold standard in subpopulation evaluation. However, does improving WGA always improve other meaningful metrics? We first show that improving WGA could lead to improved performance for certain metrics, such as the adjusted accuracy shown here. However, if we further consider worst-case precision, it surprisingly shows strong negative linear correlation with WGA. This reveals the fundamental limitation of using only WGA to assess model performance in subpopulation shift. A well-performed model with high WGA can, however, have low worst-case precision, which is alarming, especially in critical applications such as medical diagnosis. Our observations emphasize the need for more realistic evaluation metrics in subpopulation shift. We also show many other metrics that show inverse correlation with WGA in our paper. We have presented a comprehensive framework as well as a fine-grained analysis for subpopulation shift. For more details, please see our paper, project page, and code repo. Thank you for listening.